Hello and welcome back to this tutorial again. In this part we will focus on kinematics. My name is Dr. Garuma Abdisa. First, let us see motion in a straight line. Position, distance and displacement. A particle's position x is the location of the particle with respect to a chosen reference point that we can consider to be the origin of the coordinate system. For example, this car is now at position A, and sometimes later the car will be at a new position which is called position B. Previously it was at a position of 20, now it is at a position of 60 on this coordinate system. Assume this is position A, this is position B. This path is called distance, and this path in a straight line is called displacement. Distance is the length of a path followed by a particle, and displacement is a change in position in some time interval. Speed versus velocity. The average speed is the total distance divided by the total time. So the average speed is equal to the total distance divided by the total time. On the other hand, the average velocity is defined as the total displacement divided by the time taken. So the average velocity is the change in displacement divided by the change in time. And you have to make a distinction that V subscript AV for the average speed has no arrow over it because the speed is a scalar. But V subscript AV for the average velocity has an arrow over it because velocity is a vector. Let us see some kinematic equations. Acceleration is the rate of change of velocity with time. So acceleration is mathematically defined to be v minus u over t, where v is the final velocity, minus u, which is the initial velocity, divided by t, which is the time taken. And displacement is the average velocity times t. For the sake of simplicity of writing the equations, in this case we have omitted the arrow for both displacement, velocity and acceleration. And the average velocity is the initial velocity plus the final velocity divided by 2. This is simply the average. And I encourage you to remember only these three equations in order to understand the equations that involve in kinematics. So we will use those three equations that I have introduced to you a while ago in order to derive the other kinematic equations based on these three basic kinematic equations. The first one is the final velocity is initial velocity plus acceleration times time, which is directly coming from this equation. The second one is displacement is equal to the initial velocity plus the final velocity over 2 times t, which is the combination of these two basic kinematic equations. And we can write this equation as S is equal to u plus the one which is written in red is directly coming from this one and these two equations. And this can be further simplified as displacement is equal to ut plus a half at squared. And making t the subject of the formula in the formula for acceleration is equal to the final velocity minus initial over t, we can write t is equal to v minus u divided by a. So the displacement is initial velocity plus final velocity over 2 times final velocity minus initial velocity over a. So by multiplying these two terms in the parentheses, we find that v squared minus u squared divided by 2a is a displacement. Or by readjusting this formula, we can write v squared is u squared plus 2as. So we found v, which is the final velocity, is initial plus at. Displacement is initial plus final over 2 times t. Displacement is initial velocity times t plus a half at squared. Final velocity squared is initial squared plus 2as. So we will apply for any object that is freely falling or thrown vertically upward or thrown vertically downward or thrown horizontally, or even in projectiles after some little modifications that I will show you every one of them, one after the other, that everything is based on these equations. And still keep in mind that those equations are also based on another three basic kinematic equations. If you follow along, then you can understand every kinematic problem in a very systematic way. The important tip in problem solving strategy in my own experience is choose the coordinate direction in which the object is moving as positive. For example, if an object is freely falling, take the downward direction to be positive and the upward as negative. If the object is thrown up vertically into the air, take upward as positive and down as negative. If you always choose the coordinate direction in which the object is moving as positive, then it will help you to tackle the problem at ease. So let us see a case of free fall. Free fall is a case of motion with a constant acceleration. The magnitude of the acceleration due to gravity is a positive quantity g. The acceleration of a body in a free falling case is always downward, and the g is 9.8 meters per second squared, or 980 centimeters per second squared, or 32 feet per second squared. Modifying the equations for a free fall, take downward as positive, and in the case of free fall, initial velocity is 0. You replace s by h and a by g. Then these are our kinematic equations. Then in the case of free fall, this v is equal to u plus at becomes v is equal to gt because initial velocity is 0. This equation s is equal to ut plus half at squared. By substituting s by h and a by g becomes h is half gt squared because we are considering downward as positive. And this equation becomes velocity final square is simply 2gh. I'm simply getting these free fall equations from these very basic kinematic equations. Now let us modify the equations for something which is thrown downward. Take the downward as positive and once again replace s by h and a by g. So these are our kinematic equations, and it goes on like this. The final velocity becomes u plus gt. And from the second kinematic equation, h is equal to ut plus a half gt squared. Remember that in this case, it's not a free fall, but rather it is thrown downward, means the initial velocity is not 0. The third case becomes final velocity square is the initial velocity square plus 2gh. Modifying the equations for something which is thrown upward. In this case, we take upward as positive and we replace s by h and a now not by just g but by minus g. So these are our kinematic equations once again. And now it becomes v is equal to u minus gt. In the case of something which is thrown downward, this part was v is equal to u minus gt. A lot of students usually make a mistake because they simply keep one of the formula and they want to apply that same formula for everything. But if you know how to readjust or modify the formula in order to comply to different cases of the motion, then it will be very friendly and you can solve the problems very easily. In the second case, h becomes ut minus a half gt squared. In the case of something which is thrown downward, h was ut plus a half gt squared. In this case, v squared is u squared minus of 2gh. Let us see something which is thrown horizontally. Modifying the equations for a horizontal throw. In a horizontal throw, if something is thrown this way, what happens is that because it is thrown completely horizontally, the x component of the velocity is u, and the y component of the velocity becomes 0. This is a two-dimensional motion. I brought it here only because I want you to compare and I want to teach you how to make some modifications to the kinematic equations so that we can even solve these kind of problems, but this is in fact a two-dimensional problem. So in this case, whenever we try to modify the equation for such a horizontal throw, what happens is ax is equal to 0 because the acceleration due to gravity is always downward, and horizontally along x, the x component of gravity is always 0. And ay is equal to g because I'm taking downward to be positive once again. So we have the x and y components. In this case, vx is equal to ux plus axt. Vy is uy plus ayt. So vx is equal to, because ux is simply u, vx becomes u, and vy is uy, which is simply 0. And the same is true for displacement components. We write same component-wise like this. and upon reduction, because ux is simply u and the ax is 0, my x simply becomes ut. Why? Because uy is here is 0, and my ay is simply g, y becomes half gt squared. And for the third kinematic equation, we again write same with component-wise, and then in this case, the x component is ax is 0, here ux is simply u, so vx simply becomes u, and for this case, final velocity square becomes equal to 2 times g times h, because ay is simply g, sy, that is the y component of the displacement, is simply the h, that is a y, or you can call it y or h. As an example, let us see some example of what we have been talking about. Generally, in case of kinematics, if there is some story building and of a height h, and there is some ball on top of it, the ball is thrown straight up, and then on its way down, it just missed the roof of the building, and it fell on the ground. We are asked to show that the total time t is u over g into 1 plus square root of 1 plus 2gh divided by u squared. If we consider this point to be A, that point to be B, then from A to B the motion can be considered as an upward thrown object. From B to C, you can consider that interval of motion as a freely falling motion. From C to D, the motion can be considered as a downward thrown object. At the top, the final velocity is 0, so T between A and B becomes simply U over G. From B to C, for the freely falling case, and the time elapsed between A to B is actually equal to the time elapsed between B to C. But if you are not convinced with this, you can possibly do that y, that is this y, that height above the building is equal to ut minus a half gt squared, which is 0 whenever the ball is back to C, that is back to the same level it started with. Then t from A to C becomes 2u over g. And in fact, the time from A to C is now 2u over g, because the time from A to B and the time from B to C must both be equal, and u over g plus u over g is actually 2u over g. From C to D, that is the downward motion, I will consider down to be positive for this interval, and I will let h to be equal to ut plus a half gt squared. This is in the form of a quadratic equation. A quadratic of this form will have a general solution by plugging into this quadratic formula. Because time can never be negative, and this discriminant has no chance to be negative, and I will only consider the positive part of it. So t from C to D becomes minus u over g. I will split up this equation into two parts, minus u over g plus 1 over 2g into the discriminant part. Thus, t from A to D, that is the total time, becomes time from A to B plus time from B to C plus time from C to D. We add these three different times in order to get the total time. Or possibly, because I at once got time from A to C to be 2u over g already, plus t from C to D, by adding them together, we will get t from C to D to be this part. And the t from A to D is 2u over g. 2u over g is the time from A to C, plus only the last time added to it. Now t from A to D becomes 2u over g plus this part. This part is time from C to D. And then with a very little algebraic manipulations, we will get, because 2u over g minus u over g simply becomes u over g. And I will factor out this u over g term. U over g into 1 plus, then 1 over 2u will be left here. This 1 over 2u will be back into the square root. It becomes 4u squared. So 4u squared over 4u squared becomes 1. 8gh divided by this back into the square root, under this one becomes 8gh over 4u squared. So it becomes 2gh over u squared. So this is simply the proof of for something which is thrown from the top of story building, and on the way down it just missed the roof and it fell onto the base. That is the total time.